So second point. So take some, I'll call it E because this reminds me of a notation for Castelnuovo-Mumford regularity. Take some E with the following properties such that, so I need it to be big enough, but that's not essential because if one is good, then everything that's higher is still good. So you may also assume that it is at least n plus 1. Sorry. So this is the first thing. And the next, which is the important thing, is the following. Hi x ox e minus I. So this is how it works. Is 0 for any I positive and up to n, because the last you have to be with the indices between 0 and the dimension, right? Okay? Okay. Take some E. This, let me repeat, this has the right to depend on n, but not on anything else. So it should be kind of universal. Good. Very well. Now comes one good news, namely, I have not yet used the fact, in this context now, that the variety is not of general type. How to use this? Because the definition, well, any multiple of the canonical is not a birational map. Boo. It does not seem very sexy, right? But the solution is very easy. So I want to have this cohomology vanish also for I equal n. Let's look. What about Hn? Well, this is by Serre duality, right? This is an H naught of x and Ox. What do I have to put here? K, right? And then the dual of this guy. So plus I minus A, right? But, sorry, I is n. Thank you. So plus n minus E. Okay. N minus E is negative. So this fellow, n minus E H, of course. Yeah. So this fellow is negative. Okay. Okay. But now, either this is 0, so that's what I want. If this is not 0, then this means that K plus n minus A E H, this being negative, is linearly equivalent to some positive divisor, right? Right? This means K is D plus E minus N H. Now this is positive. Right? Hey, sorry guys. If K is like this, then the manifold is of general type, because outside the support of D, this is very ample, so it gives an embedding. So, right? So this would imply X of general type. So this is one of the tricks. So actually, since I assumed X to be of non-general type, this vanishes too. So what I know is that Hi X Ox E minus I is 0 for any positive I. Because I treated also the case I equal n, which is not allowed by the hypothesis. So remember that arithmetically coin Macaulay or whatever concerns only intermediate cohomology between 0 and maximum without taking them. So 0 I'm not interested, and the last one is recovered. Okay? Now, notation. Consider x0 to be x and xj to be x intersected with j hyperplanes in general position. So by Bertini, you have something smooth. Okay? Okay. Then an easy induction, so claim, use these standard exact sequences OJ, let me write it properly, OX, yes, so this is just the standard sequence of the hyperplane section, twisted by what it should, right? So if you erase this things, this is O minus 1, which is exactly what is written here. Xj plus 1 is a hyperplane section of xj by the j plus 1's hyperplane, right? So no problem. Then induction, and using this and induction implies that you will have HA xj Ox E minus I xj E minus I equals 0 for any I smaller or equal n minus j, n positive. So that's an immediate induction by the long exact sequencing cohomology. Okay? Now it looks a bit mysterious. You may say, well, so what? And now you will understand what's a miracle. The miracle is the following. Let us exploit this for j equal n minus 1. So now take then what is x n minus 1? This is x cut. This is a curve, right? It is a curve section. Right? You cut until you get a smooth curve. Okay. So now, what do you get? So j equal n minus 1. So I have the right to take I up to n minus n plus 1. This is 1. So 1. So now for h1 x n minus 1 O x n minus 1 of what? Well, E minus 1. Right? Is 0. Okay? Now I am on a curve. So this is a curve C. I change a bit notation just to evoke Riemann-Roch without any psychological difficulty. So H1 is 0. So Riemann-Roch on C gives H naught C. And this fellow, OC of E minus 1, is its degree. What's the degree? It's E minus 1 times the degree of the curve, which is the same as the degree of x, because this was obtained by cutting, plus 1 minus g. G is the genus of C, of course. And that's it, because H1 is 0. Moreover, this guy is positive because E was big enough. It is, well, of course, right? But this is positive. Good. So this is positive, right? It's a positive multiple of the hyperplane section, right? Okay. So this may be written by putting G on the other. Leave some space here, please. So G smaller, E minus 1, D plus 1. Okay? But now, this sectional genus G is related by the adjunction formula with these numbers. So this is nothing but, so actually, okay, 1/2 k h n minus 1. If you want, maybe I can write it this way. K plus n minus 1 h times h n minus 1. This is the formula, and there is a, how is it? This is 2 times, so there is a plus 1 here, okay? That's the adjunction formula, nothing more, okay? Now, this one is not relevant. What is relevant is k times h n minus 1, right? So this is n minus 1 times d, right? So this guy will be smaller than 2 times. Numbers are not important, but I'm trying to do my best. Minus n minus 1 d. And this is 2 times e minus 2 minus n plus 1, which, well, you can write like this, times d. This is the number a here, and you apply the first step, right? And you get the boundedness by the first step. So you take this coefficient, you take this coefficient to be the a, and you go here, and you apply the previous step. And you get the formula that is written: d smaller than 2n plus 1 plus a, everything at the power n. Remember that this a had to be only a function of n. Actually, it is a function of n. Where is it? Where are you? Ooh. Here. And of e. And e is also a function of n, of course. For instance, for arithmetically Cohen-Macaulay, you just take e equal n plus 1 to ensure this condition. All the rest is trivial because you have all vanishings. Okay? So arithmetically Cohen-Macaulay, maybe here. For ICM, just take e equal n plus 1. And it's okay. But I prefer to show this because this shows that essentially whenever you have a uniform bound for the vanishing of the cohomology for all varieties in question, you get boundedness. And this is a proof. Okay? There are some serious theorems that are used, and there are some manipulations. And so I think this is something that it should be further exploited. We were not, this last part is not written in the paper. So that's why I wanted to write it for you with all details. It's not, we realize that we should have written it like this after the paper, you know, it happens to everybody. Okay, so this is the story about this problem. Now, some comments. One comment is that you can try to do something more, namely this, you see, all this reasoning was numeric. But the hypothesis we used was not of general type. This is not numerical. This is linear, right? This is a linear property. There is no characterization, numerical character of being of non-general type, right? Unfortunately, I should say, right? If you know that the canonical divisor is nef, there is, because it has to be big. That, you know, but that is to say that self-intersection to be positive, right? And this is numerical. But we don't know that the canonical is nef. So this is kind of frustrating. What would be the most natural statement? In my opinion, the most natural statement would be same, but instead of non-general type, say canonical not nef. Okay, let me, can I erase everything? Yeah. Okay. So some speculations, but here these are real speculations, and you'll see why in a moment. Here at least we have a result. We proved it with all details. And at first sight, the proof may seem a little bit not unnatural, but tricky. But if you think a bit more, you'll see that each step is quite natural. That's exactly what you should do. So possible improvement. Replace not of genotype by K not NF. This is stronger. This is stronger. And the better news is that this is completely open even for surfaces in P4. I think I was one of the first who asked this some, how many? 25 years ago. Because let us think about surfaces in P4. So we know that if the degree is big enough, they are of general type. Okay. What means canonical not NF? This means either ruled, so not of general type, so you see, you recover the previous, or not relatively minimal. That is to say, the surface is the blowing up of another surface in a point. Or what is the same, there is a -1 curve. Okay? Okay? So question, is it true that in P4, any surface which is blown up of something has bounded degree? Completely unknown. Worse, let us look at the first case that interests many people around me, some old friends, old as friends, not as people. Let us stick to the case, the -1 curve, the exceptional locus of the blowing up, is aligned, that is, has degree 1. Such curves appear if you take a surface in P5 and you project it from an inner point to P4. These are extremely interesting and have been classified in the thesis of Ingrid Bauer, Cataneza's wife, so be careful because he will be here. Okay, and there are finitely many. But the better news is that it may happen that a surface in P4 has a -1 curve of degree 1, that is a line, which is not the exceptional locus of an inner projection of a surface from P5. So even, and these are not known to be bounded. So this is, absolutely you should commit suicide, mass suicide. Because it's such a natural and apparently easy question that has only been solved with some trouble. The paper by Ingrid is in Krelle, and it is quite consistent, right? And essentially, there are some classical examples of surfaces that, first famous theorem, we shall speak about this in the third lecture, is that the only surface that projects isomorphically from P5 to P4 is the Veronese surface, the famous Severi theorem. Now, what about inner projections? The answer is known, and it is given by Ingrid Bauer. There are finitely many, right? So this is the content of his theorem. It is kind of generalization of the Severi theorem when you consider inner projections instead of exterior projections. Okay? But the problem, even for lines, I repeat, -1 curves which are lines, if such surfaces are finitely many, finitely many families, is open. So the general case is when the -1 curve can have any possible degree, in principle, right? So that's why we stick to the previous version of the theorem, because here you know something. Here, if even for surfaces in P4 you don't know, it's kind of hazardous to make expectations. Okay? Now, let us speak about the second expectation. Can we please reduce some more the temperature, because first I was suffering from cold. Now I'm suffering from hot. So, first I will tell God it's too hot in hell. So he will put me in some refrigerator. The second one is connected with the Barth-Larsen theorem I started with in the following sense. So, expectation. This is some common thought with Thomas. The general expectation should be like this. So, if I is the first index not covered by Barth-Larsen, the HI should be bounded. Of course, as before, by a function depending only on the dimension. Actually, this is not the expectation. This is a philosophy. The expectation is more precise, because this is too much. So let me exemplify. It is a fascinating open fact that for surfaces in P4, what is H1 of OX? The irregularity, right? The irregularity is at most 2 in all known examples. So, example. So you see, small codimension. Of course, small codimension, this was absolutely, because I was talking about the Barth-Larsen. So, surface in P4, n equals c equal to n minus c is 0. So the first index non-covered by Barth-Larsen is 1. So the irregularity of any surface in P4 should be bounded by a universal constant. That's the expectation. But nobody knows to prove this. Not even for surfaces in P4. So, as I told already, if you don't have some cases where it is a theorem, I don't like to make conjectures. So this is too bold, right? But this is a striking fact, that no one was able to construct a surface having irregularity at least 3.
Yes, it's irregularity.
Irregularity. Yeah, it's Q. This is Q. Yeah. This is. Well, compared to Korean characters, this is piece of cake. No. So, you know, it's exactly this guy. Okay? So, we made a conjecture in this sense, but only in some cases where we were able to prove positive results. Namely, and here comes the expectation, there are two of them. First, let me recall a classical and very important definition, I think. So, X is a scroll if X is a projective bundle over some guy of smaller dimension. So if you want rank of E rank at least 2, okay, which is embedded such that the fibers, which are projective spaces, are linear. So fibers of pi linear spaces. This is a scroll. Okay? The converse is trivial. If you have a variety which fibers over y and all fibers are linear spaces of the same dimension, then you take O of 1, you take push forward, and this gives you the boundary. Okay? Such that X is isomorphic to P of V. So, okay? So we studied these particular classes of scrolls, and I think here the conjectures are, the expectation is sensible. And first, an exercise for the students. The exercise tells you the following. So assume X in P2, so Xn, dimension n, remember, 2n minus 1 is a scroll over a curve C. So scroll over C, curve. Then, you know the answer? You should. There is only one such. This. Yes. So prove this. That's an exercise. So you see here we have there are two cases left. So either n equals C, so capital N equal 2n, or 2n minus 1, or stop, because then Bart Larsen tells you that the Picard group is cyclic. So X cannot be fibered. Okay? So scrolls over curve either are like this, or else here comes our expectation. So X equal P of V, scroll over curve C in P 2n. Okay? Scroll over curve. Then, so look, again, the first obstructed index is H1, right? So then H1 X of X should be bounded, and we tell it should be bounded by 1. Now, have you heard about Leray spectral sequence? If not, just relax. But just for the students, Can you tell me who's this guy? So this is a fibration. All fibers are kind of trivial, are projective spaces of dimension n-1, right? So since H1 vanishes on all these fibers, right? The H1 can be moved from upstairs downstairs. So this is the H1 of the base, and the H1 of the base is the genus of the curve. So what I pretend together with Thomas, sorry, the point 2 will be here. What I pretend together with Thomas is that the only existing scrolls in small codimension over a curve are rational or elliptic. But these are completely classified because vector bundles of the projective line split completely into a direct sum of line bundles, Grothendieck's theorem, and vector bundles over an elliptic curve were classified by Atiyah in one of his first papers. So these we know. So if true, complete classification. So this would be very nice. And I wrote a paper with Thomas in which I studied such vector bundles over curves which give rise to scrolls, which could be called very ample, right? Because here O of 1 is very ample, not only ample, but very ample because it gives an embedding, right? And we produced some nice result. And as a corollary, it is true, this I know, if n is 2, 3, or 4. So we found some miraculous inequality. We combine it with a Castelnuovo bound for the genus of a curve, and the two curves intersect, and this gives the result for small values of n. So it is true for surfaces in P4, for 3-folds in P6, and for 4-folds in P8, which are scrolls over curves. This, I believe it should be true in general. But the proof is, sorry?
That is not yet classified.
No. It should be if this is true. No, I mean, if this thing is true, then a complete classification, no problem. This thing is true if n is 2, 3, or 4. This thing, the expectation.
It's only true for any scale, right? 2, 3, 4, right?
It's true only for surfaces, 3-folds and 4-folds. I mean, it's true. It's known only. It should be true for any n. That's the expectation. It should hold unconditionally. And we had, we very much wanted to prove this. And I think this is a problem I sought most in my life without making other progress than this. And I was quite pissed off by that. So you need some fresh idea, I think. You need some fresh idea. But this would be extremely interesting. It relates to, these are, of course, if n is at least 3, these are dual defective, right? Because are scrolls over curves. So this relates to many things that we shall study in the following lectures. But as a statement in itself, I think this is extremely interesting. And if somebody is interested, I can give references to what is known. Okay? In particular, my paper with Thomas, which is another one than the previous thing, where we proved some general result that implies the expectation for these 3 values of n. Actually, the case n equal 2 was proved previously by Lanteri and Aure, and this was done by Thomas alone. And then we found some machinery that gives this on one line with a uniform proof. But the two curves intersect when n is 4. After that, you don't know. It's I can't believe that there is a counterexample to this. This would be very bad news for me. Okay? And finally, I would like to give a similar thing for surfaces. Scrolls over surfaces. And now, this is a scroll over surface. So scroll over surface. But I want this to be in 2n minus 1. You see, not in 2n. In 2n it's a mess. Too complicated. And now, what the conjecture should be? Wait. Now here, dimension is codimension plus 1. So the first index not concerned with by the Bart Larson is 2. So here we should have that H2 XOX is at most 1, the same bound. And that's, I think that's not a coincidence. Now guys, wake up. Who is this guy? Remember what I told you. So this is a fibration, right? Fibers are trivial, meaning no cohomology there. So you can push forward the H2 from upstairs downstairs. So this is H2 of OS, right? And this is the geometric genus. You are not a student, but better than nothing. This is a geometric genus of the surface. Exactly. Okay? So that's a conjecture. And here we have very good news. So if true, we already did a complete classification. So if you want, if you moreover assume that this holds, complete classification. And the list is wonderful because it has only 4 members, which are very sexy. The first one is P2 times Pn minus 2, which stays in P3n minus 4. This is Segre. But then it can be projected isomorphically where it should, namely to P2n minus 1. Okay? It is not linearly normal. It's a projection. The other are linear. This is a determinantal variety. The base surface is also P2. And if you like, I can describe it. So you take OP2n minus 1 at the power 3 and take here some generic morphism phi in OP2n minus 1, 1. How many times? N plus 1 times. So this is a huge matrix. And you take the degeneracy locus. If you take phi generic, the degeneracy locus is smooth and blah blah, and this is your scroll. Okay? If you want, I can put the degrees also if you are interested. So here the degree is n times n minus 1/2. Here the degree is, they are nice numbers. And there is some arithmetic involved when you classify them. This is the second. Now the third is S is a K3 surface. And the degree is n squared. That's beautiful. And Mukai, stimulated by our research, proved they exist for any n. And the last is a very exceptional one. It is called the Bordiga scroll. It has dimension 3. So it is in it has degree 7. So x is in P5. And it is a scroll over P2. Again, not over P2, sorry. Over surface S, where S is in P3, a cubic surface. Smooth, of course. Very, very nice. Very nice. So this would be the complete list. So you see, such boundedness results, that's kind of the philosophy. Once you have proved the boundedness, you can expect them to classify them, because you have finitely many cases, and they should be kind of God-given. They are rare enough to be classified, and so you obtain some nice lists. Problem? I can repeat. So the last case is called the Bordiga scroll. It's an Italian object dating back to the 19th century. It has degree 3, and it is a P1 bundle over a cubic surface. Okay? S is the base. And since the dimension is 3, the fibers are P1s. So, okay? Bordiga scroll. Okay? Yeah. And those K3 surfaces, it was known, for instance, when n is 3, because in P5, these special objects were kind of classical. But Mukai proved, unpublished, that they exist always. So this is kind of a nice list, I think, right? You see, they are very, very special. It's P2, the cubic surface, and K3s, so as base. So, and of course, P2 and the cubic surface are rational surfaces, so PG is 0, right? And for K3s, PG is 1, right? So this shows you that in all known examples, PG is 0 or 1. And the expectation is that this holds unconditionally under these assumptions. My friends, I had prepared something more, but looking at your eyes, something tells me that it's not a bad idea to stop. Huh? What do you think? Huh? Okay. Tomorrow is another day.
Oh, yeah.
Tomorrow I will count, because 10 minus epsilon. Let's hope it will be an epsilon and not an O of capital N. Okay? So this is wow, my pleasure. Thank you.
So if you have a